Okay, before that, can I get your response whether you can see my screen and you can listen to my voice?
Can listen and can see the
Pardon?
we can see the slide and we can hear Dr.
Okay, thank you very much for your response. And if there's technical problem with my internet connections, please inform me as soon as possible through the WhatsApp group. Sometimes I will be disconnected from the Google Meet, maybe due to the internet connections and also network problem. So if that happen, please remind me through the WhatsApp group so that I can join the Google Meet again. Okay. So today we will continue with chapter 3 regarding the AM receiver. Okay, amplitude modulation receiver. So last week actually we have gone through these slides. Okay, so this is the type of AM receiver. So there are two types of AM receiver. The first one is what we call as the tune RF receiver. Okay, so this tune RF receiver would be the simplest limit to single channel low frequency applications, and it has high sensitivity. Among the disadvantage of this type of receiver is that the bandwidth of the receiver is inconsistent and varies with the center frequency when we tune over a wide range of input frequencies. So therefore, the selectivity of the receiver will be changed depending on the situations. And then it is unstable due to large number of RF amplifier, which is arranged as a cascaded amplifiers, and all tuned to the same frequency. So this will disturb the oscillation frequencies selectivity. Gain also is not uniform over wide range of frequencies. So this type of receiver we can see from here. Uh, so there are a few sections in this tune RF receiver that we can see. So first of all, we can see that the antenna receiver. So antenna will receive all the frequencies band. So for example, for AM frequencies, which is between 535 until 1605 kilohertz. Okay, so the antenna will receive all the frequencies, and then it will go through the RF sections, radio frequency section. So the RF section will amplify the input signal. So there are three cascaded amplifier. Okay, all of them will amplify the input signal, and then it will be passed through the audio section. Okay, so if you see the dotted line here, so that means all the amplifiers, okay, are gang tuned to a same frequency. Okay, so all the amplifiers will be tuned to the same frequency. What does it means? So for example, if I want to listen to a specific radio station, for example, radio channel A, for example, at frequency, for example, 900 kilohertz. Okay, so when I want to listen to this radio channel, okay, so I tune the receiver, and what happened is that all the amplifiers will also tune to the same frequencies. So this is what we call as a gang tune for all the amplifiers. So we need to amplify the input signal because the received signal has undergone a lot of attenuation process. So the amplitude of the received signal is very low. So that's why we need to amplify the input signal. Okay. So after amplifications, we pass through the audio sections. So if you see the here audio detector. So audio detector means um, this is the demodulator. Okay. So the word detector here means demodulator. Okay, so demodulator will do the process of demodulation. Okay, demodulation of the AM signal, and then we pass through the amplifier to increase the amplitude of the signal, and then we pass through the speaker to the output. Okay, and you also see the word non-coherent. Okay, non-coherent means that we are not using the carrier frequency properties for the demodulation process. Okay, so you're going to see that in this receiver, we are not injecting additional frequencies to the system. Okay, so non-coherent in this scenario means that we are not using the carrier frequency to do the demodulation process. Okay, and we're going to go through the second receiver type, what we call as a super heterodyne receiver. So the word heterodyne comes from a Latin word, means that mixing of two frequencies together. Okay, so the word mixing means that heterodyne. Okay, heterodyne means mixing. So when we mix at least two input together in a nonlinear device, it will um translate to another frequencies at the output. Okay, so super heterodyne means that we are using the process of mixing to produce the desired output. Okay, so super heterodyne contains a few sections in the receiver. Okay, the first section is what we call as the RF section. Okay, so the RF section contains one of the component is the RF amplifier, which will amplify the input signal because the input signal is very low and we need to amplify it before we do the next process. Okay. So this is the RF. This is a super heterodyne receiver block diagram. Okay. If you see in the receiver, as we have seen that the RF amplifier is this one, the RF amplifier, which is in the RF section. Okay, so in the super heterodyne receiver, we have four sections. The first one is the RF sections. Okay, and then mixer converter section. Okay, so this is section number one, section number two, and the third section is intermediate frequency section, IF section. Okay. And then it passed through the last section, what we call as the audio section. Okay. So if you see from this block diagram, the antenna will receive all the frequencies. Okay. From 535 until 1605 kilohertz. Okay, antenna will absorb all the AM band frequencies. However, we don't want to listen to all the radio channel. Okay, so when we open our radio, okay, when you want to listen to radio stations, for example, like previously, I want to listen to radio channel A, for example, which has a frequency of 600 kilohertz. Sorry, Previously, how much? 900, right? Okay, 900. I'll use the same example, 900 kilohertz, for example. Okay, so when I tune my receiver radio, my receiver to a 900 kilohertz, I'm actually giving the instruction to the receiver. Okay, so I'm giving the instruction to the receiver to tune, okay, to the 900 kilohertz. Okay, so the pre-selector here is a set of filtering process. Okay, pre-selector contains set of filters that will tune to the desired frequency. Okay, so that means if I want to listen to 900 kilohertz radio channel, what happened is that I'm giving the instruction to the pre-selector to tune at the center frequency of 900 kilohertz. Okay, so when I tune my radio to a 900 kilohertz, I'm actually giving the instruction to the pre-selector. Pre-selector tune to our 900 kilohertz. That means pre-selector will make the 900 kilohertz to be the center frequency, and we're gonna have this limited size of bandwidth frequencies centered at 900 kilohertz. Okay, so whenever we give the instruction to the receiver, tune at 900. If you have a radio car, for example, you tune your radio to 900 kilohertz. That means you are giving the instruction to the pre-selector. Make sure the center frequency at 900, so the pre-selector will sorry. So if I'm tuned the radio to 900 kilohertz, that means I'm giving the instruction to the pre-selector. Pre-selector tuned to 900. That means the center of the frequency would be 900 kilohertz, and it will let through. It will let the frequencies around 900 kilohertz to pass through it. Okay, so initially, if you see the antenna receive from this one, right? Antenna receive from 535 until 1605 kilohertz. So when I give the instruction, I want to listen to 900 kilohertz. So the pre-selector will set the center frequency at 900 kilohertz and limit the bandwidth to a specific bandwidth and let it pass through the system. Okay, so now I only select this portion of frequencies to pass through the pre-selector and go through the RF amplifiers. Okay, so pre-selector will limit the amount of bandwidth that it will process in the receiver. Okay, because when we want to listen to a radio station, we don't want to listen to the others. Okay, we only listen to one radio station at a time. Okay, so whenever we give the instructions, that means that would be the center frequency of the pre-selector. Okay, similar, when we tune to the pre-selector, the local oscillator also will varies according to the setting. Okay, so this frequency band, okay, centered at 900 kilohertz in my example, will go through the RF amplifier, and it will only amplify the signal that we pass through it. Okay, and then it will pass through the mixer converter section. Mixer converter section contains two input. Okay, one from the RF frequencies. Okay, RF frequencies is this one. This is the radio frequencies from 535 until 1605. So the RF frequencies that pass through the mixer converter is actually this one. Okay, so it will pass through the mixer converter sections where it will mix with the local oscillator frequency, uh, which is FLO. Okay, so FLO normally higher than the RF frequencies, all the RF frequencies. What is the RF frequencies? This one. All the frequencies received by the antenna is the RF frequencies. Okay. So if you see from here, the symbol of X, okay, means that this mixer will do the process of multiplication in time domain. Okay. So when we multiply, for example, sine and sine or cosine and cosine signal, what happens is that we're going to produce two sidebands. Okay. If you remember previously, when we do the calculation of mixer, when there is a two input inside a mixer, that means it will do the process of multiplication. For example, sine and sine function. Sine and sine function will, when we multiply sine function, and then it will produce cos minus cosine function. Okay, that means over here we are producing two sideband. Okay, okay, so this is the uh, upper sideband FUSB, and this is the FLSB. Okay, so uh, the main reason of the mixer converter, the main purpose of the mixer converter in this slide is actually to down convert the frequencies. Uh, that means we want to down convert the frequencies from radio frequency range into intermediate frequencies. So actually, when we produce these two sidebands, and then it will pass through the band pass filter. So what does the band pass filter will do? The band pass filter will select only the IF frequency, the lower frequency part, which is this part. Okay, this part. And it will remove the upper frequencies. Okay, so that means in the IF sections, I already have a small portion of low frequency signal from the band pass filter, okay, which is this one. So this gonna be the FIF, F intermediate frequency at the center. Of course, there's another spectrum over here, okay, which I will explain later. So this gonna be the intermediate frequencies. Okay, intermediate frequencies is a lower frequency compared to the RF frequency. Intermediate, okay, from RF band to become the intermediate frequency band. Okay, so this is FIF center, this point. Okay, the arrow here is actually the FIF center. So if I draw again, so something like this. Okay, so it is FIF center. Okay, then it's gonna pass through the amplifiers. Amplifier will increase the amplitude. Okay, will increase the amplitude of the IF frequencies. Okay, so IF frequencies is within this limited bandwidth. Okay, within this limited bandwidth, it will increase all the amplitude. Okay, so the amplifier will do that process. Then we pass through the last section, which is the audio section. So in the audio section, we will do the process of demodulation. Uh, so audio detector will do the process of demodulations. That means we are going to uh, down convert, we are going to translate the frequencies from FIF, intermediate frequency, to become F of the message. Okay, so this is the demodulation process. Demodulation allow us to produce the original frequencies at the output. So at the output of the detector, okay, at the output of the detector, that means we already produce a cosine signal at frequency FM. Okay, a cosine signal at frequency FM. Okay, so this we produce already FM, and then we amplify the signal, and then it goes through the speaker, so we can hear the output. Okay, we can hear clearly the output. Okay, which is similar to the VMT. Okay, so these are the process that happens. So I already explained all of it. And if you see one by one, the mixer converter sections, okay, as I have mentioned previously, that the mixer converter will down convert the frequency band from radio frequency to become the intermediate frequency, which is this one. Okay, so if you see from here, uh, the mixer converter, which is this one. So the input, if you see from the picture, so F input here is actually the FRF, okay, the radio frequency signal, okay, and then we mix with the local oscillator, FLO or F oscillator. So what we're going to produce is actually the upper sideband and also the lower sideband. Okay, so and then we pass through the filter to select only the lower frequency. So in this scenario, you're going to see that the FLO is designed so that it will always be more than the F input. Okay, as stated in in the last statement here, it said that F local oscillator or FO is designed so that it will always more than the F input or the FRF. Okay, so why is it like that? So it is mentioned here in this statement, FLO is usually higher than the input F radio frequency because up conversion leads to a smaller tuning range. So much easier to design oscillator that is tunable over a smaller radio frequency ratio. So there are some advantages if we use a FLO larger than FRF. So actually, you can also do FLO smaller than the FRF. Okay, this is low side injection. Sorry. This is also possible. Okay, this is also possible. However, in the real world, in the most of the practical system, we are not using this low side injection. Okay, normally it is higher than the FRF. Okay, so in the normal scenario, in the practical scenario, normally it is higher. So easy for us to do the down conversion of the input signal. So when we down convert the frequencies, okay, when we down convert the frequencies, it will be centered at the 455 kilohertz. Okay, 455 kilohertz. If you see, okay, so the mixer converter will down convert the frequency band from RF to IF, and it will be center at FIF center, which is equal to 455 kilohertz. Okay, of course, there's another frequency spectrum on the left and also on the right side. Okay, where is 455? If I relate to my picture, okay, if I relate to my picture, so FIF is actually referring to this frequency, okay, 455 kilohertz. Okay, so the center would be at 455 kilohertz. How do I know that? So 455 kilohertz is can be achieved because the circuit design, the circuit of the receiver is designed like that, as a standard, so that 455 will become the standard center frequency for AM. Okay, so if you see the last statement, so center frequency would be fixed and factory tuned. Okay, that means produced at the factory. So this gonna be effectively suppress the adjacent channel interference. ACI means adjacent channel interference, okay, because of its high selectivity. So if you want to, if you see from here, okay, so this is, we are still in the mixer converter section. So the explanation of about the whether FLO larger than FRF or lower, it is shown here. Okay, so if we use a high side injection means F local oscillator larger than the input frequency, the input radio frequency. Okay, so if we have FLO larger than the input FRF, that means we are using high side injection method. Okay, therefore, from here, you can see that we can calculate the intermediate frequency equal to F local oscillator minus the radio frequency input. Okay. However, if we choose to have FLO smaller than the input radio frequency, okay, what happened is that we can calculate the intermediate frequency to be equal to FRF minus FLO. Okay, so this is low side injection method. Okay, so as stated in the previous slide, that in most practical case, we normally use high side injection in most of practical cases. Okay, so I want to explain what I have explained last week, okay, about this scenario. So I will draw this one. Okay, so let's draw the frequency spectrum. Okay, so if you remember initially at the transmitter, okay, we want to transmit an input signal FM. Okay, and at the transmitter we modulate with carrier, okay, which is at frequency FC. So when we modulate this frequency, what happens is that, for example, we produce double sideband full carrier, for example. Okay, so we produce double sideband full carrier after the modulation process. So this is Fc plus Fm. This is Fc minus Fm. Okay, so whenever we do the modulation process, actually we are translating a lower frequency to become high frequency. So this happened at the transmitter side. Okay, so when we transmit this RF, so all of this is what we call as the FRF frequencies. Okay, so we transmit these radio frequencies into the medium and then received by the receiver. Now, when it is received by the receiver, we want to convert back, okay, to the original frequency, FM. How to do that? So the process is not straightforward. What we need to do is to down convert into intermediate frequency. Okay, we down convert into intermediate frequency. So it becomes something like this. Okay, so this is gonna be FIF center, which is stated in the previous slide, which has a frequency tune factory setting at 455 kilohertz. Okay, and then this is F QSF upper side frequency, and this is F LSF lower side frequency. Okay. So the pattern is still the same. We have lower sideband and also the upper sideband. Okay. So after we put inside the mixer converter, then it will become the IF frequencies. Okay. So this is going to be the, all of this is the IF frequencies. Okay. IF. All of these are categorized as F intermediate frequencies. Okay. So how do I calculate the intermediate frequencies? Okay. For example, if I use the high side injection, okay. For example, if FLO larger than the FRF, so this is high side injection. Okay, so I can calculate the FIF to be equal to FLO minus the FRF. Okay, so if I want to find the FIF center, for example, FIF center, this is equal to FLO minus the FRF center. Okay, FRF center. FRF center is referring to the center frequency over here. Okay, and then if I want to find the FLSF lower side frequency, this is equal to FLO minus the FRF USB. Okay, and then F upper side frequency, is equal to FLO minus FRF LSB. This is LSB. Okay. What is USB and LSB? So this is referring to the USB is this one. Okay, this one. Okay. And then for the lower sideband, okay, so this is USB, this is LSB. Okay. So this is actually referring to this part. Okay. Uh, so after we convert into intermediate frequency, so from RF to become IF, okay, then we pass through the audio section. Audio section will do the demodulation to become original signal frequency. Okay, so this is going to be the original sine wave, which is the VMT. Okay, so this is what happened at the mixer converter section. And then we pass through the mixer. After mixer converter, we translate into intermediate frequency. In the intermediate frequency, if you see, we have IF amplifier, and we also have the band pass filter, right? So band pass filter will remove the unwanted frequency, and then we amplify the signal using the IF amplifier. And then we pass through the audio section, which contains the demodulator or audio detector in the picture. In the picture, it is said as audio detector. Okay. So audio detector will do the demodulation process to produce the original signal, and then we amplify the signal to make the amplitude becomes bigger. Okay. So I want to show you this example about the mixer converter section process. So I got this from the Wayne Thomas's book. Okay, if you see Wayne Thomas's fourth edition, chapter 5. Okay, so it is about super heterodyne receiver RF to IF conversion. Okay. So I think from this example, you might get a more understanding about the process of down conversion by the mixer converter. Okay. So if you see from here, this block diagram consists of pre-selector. Okay. So pre-selector, the first one here, this is at the RF section. Okay. And then it goes through the mixer converter section, and then go through the IF section. Okay, so in this example, it only consists of 3 sections of the super heterodyne receiver. Okay, and then over here, if you see at the beginning, okay, the pre-selector is connect to the antenna. Okay, so the pre-selector is connect to the antenna, where the antenna receive all the frequency band from 535 kilohertz to 1605 kilohertz. So the antenna receive all the frequencies. However, I don't want to listen to all the frequencies. Okay, so in this example, I'm going to tune at radio channel 2. Okay, which is which frequency is 550 kilohertz. Okay, so in this example, I want to listen to radio channel at 550 kilohertz. In this example, okay, so when I want to listen to 550 kilohertz, I'm actually giving the instruction to the pre-selector to select the frequency band center at 550. So in this example, the preselector has a bandwidth of 30 kilohertz. Okay, bandwidth of the preselector is 30 kilohertz. Okay, so that means if you see from here, the preselector will limit the amount of frequencies that it will let pass through. Okay, so if I draw the frequency spectrum, okay, from 535 until 1605, okay, so I only want to listen to a specific radio. Let's say I put here 550 kilohertz. So this 550 would be the center frequency of the preselector, and it will only let the frequencies band, limited frequency band to pass through. Center at 550. Okay, so the 30 kilohertz is actually this one, this bandwidth. Okay, it will only let pass through 30 kilohertz in this example. Okay, like this. So this picture actually have been drawn in this example like this. Okay, if you see the first picture here, okay, so these are the frequencies that the preselector allowed to pass. Okay, center at 550, which is channel 2. This is the channel that I want to listen. Okay, however, if you see from here, since the bandwidth of the preselector is 30 kilohertz, it will also let pass through the channel number 1 and channel number 2. Channel number 1 is located at 540 kilohertz, while channel number 3 is located at 560 kilohertz. So the amount of bandwidth 30 kilohertz, that means the preselector in this example allow 3 radio channels to pass through it. Okay, and remember, I only want to listen to this radio. I don't want to listen to the others. Okay, so we allow these 3 channels to pass through the preselector because if you see from here, from 535 until 565, so the length here, so the bandwidth that we allow to pass is 30 kilohertz. Okay. So what happened is that these 30 kilohertz of frequency band will be passed through the mixer converter. Mixer converter, if you remember, it will convert the frequency to intermediate frequency. Okay, and here we have FLO. Okay, so this is FLO, which is 1005 kilohertz. Okay, in this example, FLO is equal to 1005 kilohertz. And if you see 1005 kilohertz is larger than all the input frequencies. Okay, it is larger than any frequency from 535 until 165. Therefore, in this example, we are using the high side injection. Okay, that means I can find all the IF frequencies using this equation, FLO minus F input radio frequency. Okay, that means all of these frequencies will be down convert into the intermediate frequencies. So if you see the first line here, what happened is that we're gonna find the first. We're gonna find the first IF frequencies. So 1005 minus 535. Okay, we're gonna start from here. Number one, number two, number three, number four, number five, number six, number seven. All seven frequencies will be down convert into intermediate frequency. Okay, so if you see from here, we are going to use this equation to find the output of the mixer converter. So therefore 1005 minus 535, we're going to get 470 kilohertz. Eh? And then number two, 1005 minus 540 kilohertz. So we're going to get 465 kilohertz. And then 1005 minus 545 kilohertz. So we're going to get 460 kilohertz. Okay, so we convert all of this, okay, all of the frequencies. Okay, so we're going to get frequencies of IF ranging from 440 until 470. That means the frequency of IF that we produce is between 440 kilohertz until 470 kilohertz. Okay, so this frequency is shown in the frequency spectrum over here. Okay, so when we subtract the local oscillator with the input radio frequency, what happened is in this frequency spectrum. Okay, so 440. So if you see that this 440 is actually comes from number 7 over here. Okay, and then number 6 over here, and then number 5 over here, and so on. So this looks like inverse. Okay, looks like the high frequency becomes the lower frequency. Okay, so I can say that maybe I can put numbers. So this is actually number 6, number 5, number 4, number 3, sorry, this is number 7. So this is number 7, this is number 7, number 6, number 5, number 4. Okay, number 3, number 2, number 1. Okay, so that's why the arrow looks like this. So this is actually channel 3. Okay, this is channel 2. This is channel 1. Okay, so it becomes like this. So all of this is IF intermediate frequency. But still, remember, I only want to listen to these radio frequencies only. Okay, so mixer converter still maintain 3 radio channel at the output. Okay, so we are still producing over here, okay, 3 channels at the output, but we already convert into intermediate frequencies. Okay, so all of the 3 channels has been down convert into intermediate frequencies. Then we pass through the IF filter. Remember, IF filter is a band pass filter stated in the previous slide. If you see, if I go back to the slide, which is this one, the band pass filter. Okay, so the band pass filter over here will select only the desired radio frequency channel. Okay, and if you see from here, the IF filter, okay, is between 450 to 460. So this IF filter will cut through the frequency from 450 until 460. That means from 450 until 460 will be selected. Okay. And if you see from here, this is the center frequency of IF. This is actually FIF. C, this is F upper side frequency, USF. This is FLSF. Okay. So after the IF filter, then we're gonna get the single frequency channel. Okay. So now at the output of the IF filter, I can listen to channel 2 only. Okay. From there, after the IF filter, then we can amplify the signal and then pass through the audio section for the demodulation process. So this is what happened at the mixer converter. Okay. And I also want to show you another example like this. So this is also mixer converter example. Okay. So if you see from here, from the picture, okay, so we are receiving this input signal between 895 until 905 frequencies band. So this is the RF frequency input. Okay, from 895 until 905. Okay, so these are the what pre-selector will do. So if you see from here, this is actually connected to the antenna. Okay, so the antenna receive all the frequency band, then it pass through the pre-selector. The pre-selector would filter the input signal center at 900 kilohertz, and it will select this frequency band. The pre-selector will select this frequency band. Okay, that means when I want to listen to radio station, I'm giving the instruction to the pre-selector. Pre-selector tune to 900 kilohertz. So when it tuned to 900 kilohertz, that means 900 kilohertz would be the center frequency of the tune process. Okay, of the tune frequencies. So these frequencies, this frequency band from 895 until 905 will be selected and then pass through the RF amplifier. RF amplifier will amplify the amplitude of the signal. Then it will pass through the mixer converter. Mixer converter has local oscillator equal to 1355 kilohertz, which is larger than the F radio frequency input. That means I can find the FIF using these equations, FLO minus FRF. Okay, so what happened is that when we subtract, okay, when we subtract the frequencies, we can find the FIF over here. Okay, so how much will be the FIF? So this is the questions in the example. If you read the example, the question, for AM super heterodyne receiver that use a high side injection has a local oscillator 1355. Determine the IF carrier, the IF upper side frequency, and the FIF lower side frequency for RF wave that made up of a carrier and upper lower sideband frequency 900 until 895, which is the output of the pre-selector. So the question asks you to find the FIF for each of the input frequency. Okay, so if you see the first one, in order to find the center of the intermediate frequency, So we use this FIF equal to FLO minus FRF. That means the FLO, okay, minus the FRF center. Okay, FRF center. Okay, FRF center or FC. Okay, the center here is, if you see from here, this is FRF center, or I can simply make it as FC to make it easy for you, FC. Okay, the center here, so we get 455 kilohertz. And then if I want to find the upper side frequency of the intermediate frequency, that means FLO minus FLSB, okay, which is 9895 kilohertz. So I get 460 kilohertz. If I want to find FIF, lower side frequency, that means FLO minus FUSB. So I get 450. So therefore, I'm going to produce an IF frequencies from 455, center at 455, and then over here is 450, and over here is 460 kilohertz. And this already stated over here, if you see from here. So we're going to produce this three component from 450 until 460. Okay, so we're going to produce this frequency band, IF frequency band. Okay, so these are all the FIF frequencies. Okay, so therefore we pass through the band pass filter. The band pass filter will limit the desired frequency, and then we pass to the IF amplifier. Okay, so that is about the mixer converter section. Okay, class, if you have question, you are most welcome to ask anytime. Okay. So if there's no question to ask, then I will move to the next parameter. Okay, the next slide about the next parameters, the receiver parameters. Okay, so in this slide, okay, in this slide, RF receiver parameters. The first one is the selectivity. Okay, so selectivity is a parameter that determines the ability of the receiver to select the desired frequency band and reject all the other unwanted frequencies. Okay, the unwanted frequency will be rejected. So how strong, how good is the selection process can be defined using the parameter of shape factor, SF. So shape factor is equal to bandwidth of minus 60 dB over bandwidth of minus 3 dB. Okay, so if you see from here, starting from this slide, this slide is actually referring to the pre-selector. Okay, this slide is showing the process, the parameter at the pre-selector. Okay, so pre-selector, if I draw the picture receiver, this receiver, this is the antenna. So the pre-selector is the front side of the receiver section. Okay, over here we have the pre-selector. Okay, so pre-selector contains a set of filtering process, set of filters to select the desired frequency. So for a filter, if you see for the filter frequency response curve, it looks like this. So this is a filter frequency response curve. Okay, so if you see, it is a bell-shaped curve. Okay, it is a bell-shaped curve, and ideally, if you see, ideally, if I have a filter, I want my filter to have a sharp cut-off frequencies. Okay, so for example, if I giving the instruction to the receiver, I want to listen to radio frequency, for example, 900 kilohertz, for example. Okay, so I'm giving the instruction to the pre-selector, resonate at 900 kilohertz. Okay, so the FR here is a resonant frequency. That means it will be at 900 kilohertz center. Ideally, okay, I want to have a filter that can have sharp cut-off frequency like this. Ideally, okay, if it is an ideal case, I can have a bandwidth like this, ideally. However, in the real world, the scenario is not like that. Okay, in the real world, you see that we have this response curve. Okay, in the practical case, it will look like this. That means we are actually selecting a bigger bandwidth. Okay, larger bandwidth. Okay, so this is the real scenario of a filter. Okay, so the side part, the side part here is what we call the skirt. The skirt over here. So this is what we call the filter skirt, the skirt over here. So ideally, we want the skirts to be as minimum as possible, to be smaller. Okay, so if the skirts is closer to F1 and F2, it would be better. Okay, the closer the skirt would be better. Okay, in the real world, we want to limit this side. Okay, if this part is minimum, that means your filter is very good. Okay, it will be sharp cut off. Okay, so if you see from here, this is minus 3 dB over here. Minus 3 dB will cut through this part, and then which is it will cut at frequency F1 and F2. This one. Okay, minus 3 dB. Minus 60 dB is somewhere over here. Okay, minus 60 dB. And it will cut through this frequency. For example, F3 and also F4. Okay, so that means bandwidth of minus 60 dB is equal to F4 minus F3, while bandwidth of minus 3 dB is equal to F2 minus F1. Okay, so this is the shape factor. Okay, ideally, we want the shape factor to be as closer as 1. Okay, as smaller as 1, ideally. Okay, the smallest value would be 1. Okay, this is the smallest value of shape factor. So the smaller the shape factor would be better. Okay, then The second parameter is okay, this is selectivity, so we are still selectivity. So the other parameter of selectivity, we have what we call as a Q factor. So Q is equal to inductive reactance. Okay, inductive reactance also in terms of ohm. You divide with the resistance also in terms of ohm. So Q factor does not have a unit. It is a unitless parameter. Then we have the bandwidth of the pre-selector. Okay, the bandwidth of the tune circuit. Okay, so you gonna heard the word tune circuit. Tune circuit is actually the pre-selector. Okay, so you're gonna see the word tune circuit after this. So tune circuit also referring to the pre-selector. So the bandwidth of the tune circuit or the bandwidth of the pre-selector is equal to the resonant frequency divided with the Q factor. Okay, so Q factor, if you divide with Q factor, you're going to get the bandwidth. What is the resonant frequency? Resonant frequency is the desired frequency that we want to listen. For example, if I want to listen to radio channel at frequency 900 kilohertz, okay, I will give the instruction to the pre-selector, tune at 900 kilohertz. That means the resonant frequency of the pre-selector would be 900 kilohertz, okay, which is the FR. So FR is the frequency of the radio that we want to listen, okay? And then if we go to the next part is sensitivity. This is the second parameter. Okay, the second parameter is sensitivity. Sensitivity determine the minimum of RF signal amplitude that can be detected at the input of the receiver, and we can produce a usable demodulated info. So that means how small would be the input signal that we can detect, so it will determine our sensitivity receiver. Okay, receiver sensitivity. So if my receiver can detect a small amplitude signal, that means my receiver is sensitive. Okay, if my receiver cannot detect small amplitude input signal, that means my receiver is not sensitive. Okay, so the smaller the size of the input signal that we can detect, and we can do the demodulation later, so that means my receiver is sensitive enough to receive small amplitude signal and still be able to demodulate the signal and produce a suitable output. So that one means define the sensitivity parameter. Okay, so we not only can detect small amplitude signal, we can detect and we can do the demodulation process and produce the desired output. So that is determine the sensitivity parameter. Then we have a bandwidth improvement factor. Okay, bandwidth improvement factor is equal to bandwidth RF divided with bandwidth intermediate frequency. Okay, so bandwidth of RF, if we see bandwidth of RF divided with bandwidth of intermediate frequencies. So if you see how can I show you? So I want to go back to the slide. I want to go back to this slide. So if you see from here, bandwidth of RF in this example is from 535 until 560. That means this is 30 kilohertz. Okay, in this example, then we down convert into intermediate frequency. Okay, so the FIF the bandwidth of, this is RF, the bandwidth of IF after we down convert is from 450 until 460. That means the bandwidth is 10 kilohertz. Okay, so bandwidth of RF you divide with bandwidth of IF, you're going to produce the parameter bandwidth improvement factor. Okay, in the previous example, as we have seen, bandwidth of RF is around 30 kilohertz. In the previous example, 30 kilohertz. Okay, so this is the output from pre-selector. Okay, the pre-selector select up to 30 kilohertz from the previous example. Then this is after the uh, this is after the uh, IF band pass filter of the intermediate frequency, IF BPF. So in the previous example, we reduced the amount to become 10 kilohertz, only one channel. Okay, so if you divide 30 divide with 10, you're gonna get 3, and then you can do the noise figure improvement. That means it is taught 10 log of bandwidth improvement factor. Okay, so you're gonna get in terms of dB. Okay, so this is how it looks. And so IF here is when we already cut off the frequencies at the IF sections. In the previous example, 10 kilohertz. And then from pre-selector, previously in the example, we get 30 kilohertz. So if you divide and then you do the logarithmic value, then you can get the noise figure improvement in terms of decibel. So we're going to go through the first example about the, this is the example of pre-selector. Okay, so if you see a high quality tune circuit, so the word tune circuit, this is actually the pre-selector. Okay, it's used to keep the bandwidth narrow to ensure that only the desired signal is passed, assuming the 10 microhenry coil is with resistance 200 resistance 20 ohm is connected in parallel with 101 picofarad capacitor. Okay, so if you do the, okay, so we have the resistor, for example, here, and then we have the inductor, and then we have the capacitor over here. Okay, so this is R, this is inductor, and this is C. So, so what is the first question? The circuit resonate at what frequency? Okay, so in order to calculate FR, F resonant is equal to square root of LC. So if you see from here, the resonant frequency is equal to 1 divided with 2 pi square root of LC. Okay, 1 divided with 2 pi square root of LC. So if you put inside the value of 100 picofarad and 10 microhenry, okay, 100 picofarad and 10 microhenry, square root, multiply with 2 pi and then 1 over this value, so you're going to get 5 megahertz. Okay, so you can use your calculator, whether you can get the value or not. So if you see from here 101.4 picofarad, you multiply with 10 microhenry, and then square root of answer multiply with 2 pi, and then 1 over answer, so you're gonna get 4998056. So it has been rounded up, the value to 5 megahertz. Okay. In exam, you should not do like this. Okay, this is just to simplify your understanding in this lecture process. Okay, so in the exam or in the test, you should write the absolute value 4998056. So it is actually 4.998 megahertz. That's the precise answer. Okay. Then the next question asks you to find what is the inductive reactance. Inductive reactance means this this XL. So this is inductive reactance is equal to 2 pi F resonant. Okay, that means it is 2 pi F resonant multiplied with the inductance value. Okay, so if you multiply 2 pi multiplied with 5 megahertz multiplied with 101.4 pico, so you're gonna get 3. Okay. So 5 mega multiplied with 2 pi multiplied with 101.4 pico. So we're gonna get 3.15 pi. Can you get to 314? 5 mega multiplied. Inductance is 10 micro multiplied with 5, 2 pi. Okay, so I get 314.159. Class, can you get this answer? Can I get your response? Hello, still, yeah. Are you listening?
Yes, sir.
Okay. So can you get the same answer? Anybody can respond? Can you get the same answer, 314? 314 ohm? So I get actually 314.159 ohm. Do you get the same answer?
Dapat, doktor, dapat.
Okay, thank you for the response. So this is the inductive reactance. And then the third question asks you to find the selectivity of the circuit. So in this example, the word selectivity parameter, this is referring to the Q parameter, okay, which is F resonant divided with the inductive reactance, okay. So so Q parameter, if you see from here, it is inductive reactance divided with the resistance, okay. Inductive reactance divide with the resistance, so you get the Q parameter. Okay, so this is 314 you divide with resistance 20. Okay, 20, so you get 15.7. Okay, 314 divide with 20, so you get 15.7. No unit. Okay, and then the next question asks you to find the bandwidth of the tuned circuit. or the bandwidth of the pre-selector. Okay, so the bandwidth is equal to resonant frequency divided with the inductive reactance. Okay, sorry, resonant frequency divided with the quality factor. This one, bandwidth of the pre-selector is equal to resonant frequency divided with the quality factor. Okay, so that means this is 5 mega. You divide with 15.7. So you get 318.47 kilohertz. Okay, so this is the bandwidth of the pre-selector. That means we have this. The bandwidth is 318.47 kilohertz. So the center is at resonant frequency, FR. Okay. And over here, we don't know how much is F1 and also F2. Okay. But we know that this one is 5 megahertz. Okay. So the next question asks you to find the upper and lower cutoff frequencies. So that means, as I stated here, the question asks you to find how much would be the lower frequency and how much would be the upper frequency. Okay, so if you see from here, the way the solution here is like this. So first of all, we divide the bandwidth with 2. So we're gonna get only half of it, either half of this or half of this. So we want to know the half distance from the center. Okay, so we divide with 2. The bandwidth we divide with 2, so we get 0.159 megahertz. So this is a half size, okay, half distance. So if I want to find F2, okay, F2 means F resonant. I add with F bandwidth divide with 2, bandwidth divide with 2, which is 0.159. So I get 5.159 megahertz. And then if I want to find the lower frequency, so the lower frequency is F resonant minus with bandwidth over 2. So I get 4.841 megahertz. Okay, so we get the lower frequency and also the upper frequency value. Okay, can you follow this example? Can I get your response?
Boleh.
Okay. Okay. So I will go to the next slide, which is about the image frequency. Okay. So the image frequency is any frequency other than the selected radio frequency carrier, that if we allow it to pass through the pre-selector, it will mix with the local oscillator frequency and produce cross product frequency, which is equal to the intermediate frequency. So that means the pre-selector must block the image frequency from entering the receiver. Otherwise, the receiver will be unable to differentiate whether this is the desired frequency or the image frequency. Okay, if image frequency is passed through the receiver, it will produce an IF frequency. It will produce a frequency similar to the IF frequency. Okay, it is the image of the intermediate frequency, where we don't want this frequency at all, actually. Okay, so remember, we need to block the image frequency from entering the receiver. Otherwise, the receiver will not be able to differentiate whether this is a desired frequency or the image. Okay, so if we go through here, okay, if you see from here, uh, the FRF, this is the input frequency. And if we use a high side injection, the FLO is larger than the FRF. Okay, so the image is located here. The image, okay, the image is located at 2 times the FIF. Okay, so we have to block this high frequency from entering the preselector. Okay, so if you see that the distance is similar with the IF frequencies, so we don't want this image to enter the preselector. So F image we can calculate equal to FLO plus FIF, okay, or F image is equal to FRF plus FIF, 2FIF, okay. So this is how we calculate the image frequencies. So the first example here, you see that determine the image frequency for a standard broadcast receiver using 455 IF frequency tuned to the 620 kilohertz. So this is the FRF, the radio frequency that we want to listen. Actually, we tune to 620 kilohertz. So if you see from here, uh, so if you see from here, you are given FIF and also you are given FRF. Find the image frequency. So over here, if you see from here, this example, try to find the FLO first. FLO is equal to FRF plus FIF. Okay. From this picture, if you see that FLO is equal to FRF plus FIF. Okay. So that's why you get the FLO equal to 1075 kilohertz. So once you know the FLO, then you can find the image. The image is located at FLO plus FIF. Okay, so 1075 plus FIF, so you get 1530 kilohertz. Okay, you can also do like this. F image will be equal to FRF plus 2 times FIF. Okay, so 620 plus 2 times 455, you will get the same answer, 1530 kilohertz. Okay, so if I try 455 times 2 and then plus 620, so I get 1530 kilohertz. Same answer. Okay, next is about image. Okay, before that, class, for your information, image frequency is among the favorite question in the exam. Okay, we have asked these questions many times in the exam, where we have asked the student to the define the image frequency. What is the meaning of image frequency? So you have to explain and you can sketch the frequency spectrum like this. Okay, so this slide has been asked in the exam in the previous semester. Okay, so it is important for you to know how to calculate the image frequency. Okay, then we have the image rejection ratio, IFRR. So it is a numerical measure of preselected ability to reject the image frequency. So the image frequency rejection is defined as alpha equal to square root of 1 plus q square rho square. Okay, q parameter square multiplied with rho parameter square. Okay, so I would suggest you to make a bracket like this so that you will not make careless mistake. Okay, so the image rejection ratio, the rho parameter here, is actually the image frequency divided with the RF frequency minus FRF divided with F image. This one. Okay, so you will get the rho parameter is the unitless parameter. Okay, then the quality factor can be calculated using the inductive reactance divided with the resistance. So please correct your notes. Okay, so this is actually not XL, it is a X subscript of L. Okay, divide with the inductive reactance, and or you can make it as F over B, okay, where B the bandwidth. So when you put all the parameters, then you can get the value of alpha. Okay, once you get the value of alpha, then you can find the image rejection ratio in terms of decibel, 20 log alpha. Okay, you will get the value in terms of dB. Okay, so if we do the example, so this example 2.13 is defined from example 2.12 from the previous example. So previous example, we know that the image, F image, is equal to 1530 kilohertz from the previous example. Okay, and then we know also that the FRF is equal to 620 kilohertz. We also know the FIF from the previous example equal to 455 kilohertz. Okay, and you also been given Q parameter equal to 40. Okay, so in order to find the image rejection ratio alpha parameter, we have to know the Q parameter and also the rho parameter. So the rho parameter, the image rejection ratio, is equal to F image divided with FRF minus FRF over F image. Okay, so if you see from here, F image divided with FRF minus FRF over F image. So we get 2.0625. Okay, then you put inside the equation of alpha equal to 1 plus q square rho square. So I suggest you to make a bracket over here so that you will not make careless mistake. Okay, so 40 square times 2.0625 square, and then plus 1, and then square root. So you will get this answer. Okay, after that, you have to calculate in terms of decibel. So image rejection ratio in decibel, so 20 log alpha, so 20 log in bracket 82.5061, so you will get 38.33 decibel. Okay, so this is gonna be how we can calculate the image rejection ratio, IFRR. Okay, so this is what we call as IFRR parameter. Okay, IFRR parameter is 20 log alpha. Okay, So can I get your response? Can you follow this example? Is it okay?
Okay, Dr. Okay.
Okay. Okay. So the second part is angle modulation. So before, after this, we're gonna take a break. But before that, I want to explain to you about the project. Remember the project? We still have the second task. Okay. So let me briefly explain about the project that you are doing right now. Okay. So if you see that we have the second task to produce the FM transmitter prototype. Okay. So the FM transmitter prototype, if you see from here, now actually we are in week number 6. So I actually should give you the briefing during week number 2, sorry, week number 4, where I forgot to give you the briefing. So I will give the briefing now. Okay. And you already submit task number 1 through the author, which I give the time until 9 December previously, until Sunday. Okay. You have submit this task number 1 report. Okay. So now we want to do task number 2. Okay. What is task number 2? So if you see task number 2, you have to go through this part. Okay. So task number 2 is FM transmitter system prototype. That means you are going to produce transmitter prototype. Okay. This is a hardware project. Okay. So the course learning outcome for this one, apply frequency modulation technique and suitable method for electronic communication system, demonstrate professionalism in the work related to electronic communication system, and then write a report and present the work related to the given project instructions. Okay. So the duration is actually from week number 4 until week number 15. So this is a group work. Okay. So this is a problem-based learning where it is a student-centered approach where you need to learn with your group members regarding the process of producing the FM transmitter. Okay, so this is a brief description about what is PBL, what is a problem-based learning. Okay, so problem-based learning, it is based on the given problem, then you have to find the solutions and then produce the output. Okay, so this is the activities for task number 2. Task number 2, so there are a few activities that you should follow. Okay, so we are already week number 6, so I suggest you should start as soon as possible. Okay, where we have in the middle, we're gonna have progress report 1 submission. Okay, progress report 1 submission, and then progress report 1 submission through the author, and then progress report 2 submission. So there are going to be 2 progress reports that you need to submit. And you also need to submit the final report later. The last one going to be the final report. So there are 3 reports that you need to submit. Okay. Progress report 1 and progress report 2 just want to know about your progress, your current progress. And then in the before you submit the final report, we're going to do the prototype demonstration, okay, in the lab. Okay, so this is going to consist of the same member from task number 1. Okay, and you should fill in this group member information, including the photo. Okay, this should be put in the final report later. Okay, put in the final report later. Okay, so this is the instruction and the PBL in-depth knowledge of frequency modulation, which is covered in chapter 3 to solve the FM transmitter communication system. Okay, to solve the problem, so the student are given range of technical specification and limitation for the FM transmitter system. Student needs to analyze the resulting input and output wave characteristic of the FM transmitter and propose a solution to improve the quality of the audio signal. Student needs to form a small group. So you already formed the small group, and then these PBL project activities involve discussion to develop the FM transmitter system. So the location, you can do it in the classroom, in the laboratories, and other places. So I suggest you to focus in the laboratories. So you can go to the project lab at C10. You can go to C10 lab, mal project. So project lab. Or you can go to the MKD. So this is at C10, block C10. Or you can also go to the MKD, Digital Communication Lab at block G1. Okay. So you might need some equipments like the multimeter, oscilloscope signal generator, spectrum analyzer, and etc. To analyze the output. So if I go through, so the instruction is actually stated over here. Okay, so this is the problem that given to you actually. So FM broadcasting, short for frequency modulation broadcasting, is a technique employed to transmit data, typically in the form of audio signal via radio frequencies. So this method, the frequency of the carrier wave undergoes variation of modulation in accordance with the changes of the audio signal to be conveyed. This modulation process means by which information such as music or speech is transmitted. In Malaysia, the FM frequency band allocated by the MCMC for the commercial radio station falls between 88 to 108 megahertz of range. Okay. And then this FM broadcasting offers both advantages and drawbacks, which have contributed to its historical importance and continued use. A common issue encountered in FM radio reception pertains to signal degradation and noise. So this is gonna be your this gonna this gonna be the limitation that you will face uh, during your activities to complete the prototype. Okay, the signal strength can vary significantly with factors such as distance from the radio transmitter, environmental conditions, and electrical interference from sources like power lines, electronic devices. Signals grow weaker as the receiver moves further away from the transmitter. So the longer the distance between transmitter and receiver, the signal will be weaker, or this is what we call as attenuation. Okay, the signal will attenuate due to the distance. Um, Making them more susceptible to noise and atmospheric disturbance, particularly during night hours when ionospheric reflection affect the signal. As a future RF engineer, so this one, as a future RF engineer, you are required to develop a set of FM transmitter for a community radio station. The receiver should adhere to regulatory requirements and provide high quality audio transmission. Okay, that means you should use the frequency from 88 until 108 megahertz. Okay, so the transmitter system should be able to transmit audio signal using the unoccupied available FM radio frequency. The transmitted signal waveform will be analyzed through the oscilloscope spectrum analyzer. You are allowed to propose any design using basic electronic components and the printed circuit board PCB. However, detailed analysis of the circuit must be included in the report. such as theoretical calculation, signal waveform, and signal spectrum before and after modulation. So the cost of building the transmitter cannot be reimbursed. As such, you are advised to use any component available in the laboratory, or you can buy it yourself. You can also take the electronic components from the faculty as well. Okay, you can go to the ECS system application where you can order the electronic component from the faculty. Okay, we have resistors, capacitors, inductors that we can give to the students for free. The rest you should buy in any local store or online store. Okay, so basically what you want to do is like this. So imagine this is your transmitter where it consists of components, basic component, resistor, inductor, capacitor, transistor, and etc. Okay, so this is your transmitter. Okay, and your transmitter, okay, will be connected to the input. Here is the signal generator. Okay, signal generator would be input to your transmitter, and your transmitter should be able to transmit at frequency between 88 until 108 megahertz. Okay, your transmitter should be able to transmit at this frequency, and this transmitter should be connected to the oscilloscope. Okay, so this is a oscilloscope. Okay, so we want to measure your output frequencies. Okay, so oscilloscope should be connected to the output, and I also want you to connect to the oscilloscope at the input. Okay, so at the input from the from the signal generator, I also want you to measure the input signal at the oscilloscope. Okay, so we can measure the signal at the input and also the signal at the output. Okay, so you should you must be able, for example, at the output at the output here, okay, at the output here, you should be able to detect to get the value between 88 until 108 megahertz in the oscilloscope. So if you can successfully produce the output in the oscilloscope, that means your project is success. Okay, that's it. So you only can use the basic component. You can only use a basic component. You can use basic component. Basic component means you are using the transistor, resistor, inductor, capacitance, and etc. To produce the output signal. You can download from the internet any design, no problem, but you must know how it works. Okay, the design is not by yourself, but you should understand about the design. So before you do this, that means I suggest you to do the simulation first using Proteus, Multisim, and etc. so that you can get the estimated output. So before you do the hardware, you should try to simulate first using a software so that you can choose the correct parameters of each of the electronic components. Okay. So this is the assessment. I will assess you through the progress report 1, progress report 2, demonstration 10%, and final report 10%. Okay. So the progress report, what should be in the progress report? So you can refer here. Okay. Basically, we want to know your prototype work pictures, video, so circuit design and etc. Okay. So refer to form B and form C. So we already give you the rubric form. So you can follow the rubric form. What is the criteria that will be evaluated in the progress report? Okay. Then PBL demo. So you can refer to form as rubric D, form D. So rubric form D contains a few sets of criteria that you will be assessed. Okay, and then the final report. Okay, so if you read from here, there are in the final report, refer to form D for the mark distribution and rubric. So the content of the technical report can obtain from the rubric D. Each group must go through the rubric so as not to miss out on important piece of information. Use the template of technical report provided. The reference section in the technical report must be referenced from the database provided by the library. For instance, the Science Direct, Access Engineering Novel, IEEE Explore, and etc. Conduct online meeting with group members and prepare the minutes of meetings, more than 3 minutes of meetings. Okay. So your minutes of meetings must come also with the picture provided. And then group reflection. So in the final report, you should add the group reflection. Okay. What is a group reflection? I think it's given here. This is a group reflection that should be put in the final report. Okay, final report. Okay. So in the final report, just need one group reflection is enough. One group reflection is enough. Okay, it's not for each of the student, it's for the group. Okay, so you can fill in these boxes. So what is the new knowledge you have learned from this assignment? In your opinion, what is the most complex issue in completing the given task? And how did your group come out with the idea of the best possible solution? Okay, so this is form A for the task 1 rubric. Okay, so this is the task 1 rubric. So this is the rubric as well. So this is a marking form for progress report. This is what? Sorry, this is task number 1, right? This is task number 1. Okay, so you already submit task number 1. So task number 1, you will be evaluated using this marking form and also the rubric. Okay, this form B is for the progress report 1. Okay, this is the marking form for progress report 1, and this is the rubric. Okay, and then this is the marking form for progress report 2. So actually the marking form you can put in front of the as a front page of your report submission. Okay, you can put this marking form in front of the as a front page of your submitted report. Okay, so each of the submitted report, I suggest you to put this marking form as the front page. Okay, for the progress report, sorry, for the task number 1, if you already submit, so no problem, don't worry. Maybe some group forget to put this marking form, so that's okay for me, no problem. But now we are in task number 2, so I suggest you to put this marking form as a front page. Okay, so progress report 1, and then the rubric, and then progress report 2 marking form, and then the rubric. So the rubric, you can see how you will be assessed. Okay, how much mark you will get based on the rubric. Okay, I will use this rubric to give you the marks. Okay, so you can follow this rubric. Okay, in order to get the full marks. Okay, And then this is the marking form for project demonstration at the end of the semester. Okay. You will be assessed. You will do the demonstration in the laboratory, and I will assess you using this marking form. And this is the marking form for the final report. It is combined here, marking final report. Okay. And this is the rubric. This is the rubric for the project demo. And this is the rubric for the final report. Okay. Finish. Okay. So, Klaus, do you have question to ask about the project task number 2 for now? Can I get your response? Do you have question or you don't have any question for now?
Tak ada.
Okay. Bagus lah, kamu selalu respon ah. Yang lain asal senyap. Bahaya ni siapa yang senyap.
Ada doktor, ada.
Ada, okey. Dia bukan apa, kalau kita bercakap seorang-seorang ni kadang-kadang macam cakap dengan seorang-seorang kat skrin ya. So kalau ada respon tu kita boleh tahulah ada orang yang mendengar, okay. So I think maybe you don't have any question about this project task number 2 yet. Maybe later you have a question, you can ask me anytime. Okay, you can ask me through the group, through the WhatsApp group is also okay. You can ask me questions, so we can have discussion. You can ask me anytime regarding this matter. So the timeline is very crucial. The timeline is very crucial. Make sure you follow the timeline. Okay, you must follow the timeline. This is the schedule. You must follow the schedule. Okay, otherwise there's gonna be big problem. Okay. So for now, we're gonna take a break. So we're gonna take a break for 10 minutes. Okay, break 10 minutes. So we're gonna start at 1. Okay. So 10 minutes break. So feel free to go anywhere you like.
Okay, doktor.
Okay. Okay. I think I should continue. So it's already 1:15. Can I get your response whether you are still there?
Yes, Doctor.
Okay.
Yes, Doctor.
Okay. Thank you. So I will continue with chapter 3. So we already finished part number 1 of chapter 3 about amplitude modulation. Now we're going to learn about part number 2 about the angle modulation. So angle modulation consists of frequency modulation, FM, and also the phase modulation, PM. Okay. So FM will be about your project. Okay. So in angle modulation, you see that there is a general equation for the angle modulation. Okay. The general angle modulated signal is given as this one. Okay. VT is equal to VC sine 2 pi FCT plus theta T. Okay. So in some other literature books, you might see that they are using a cosine function. Okay, so it doesn't matter whether it is a sine function or cosine function, both are correct. Okay, so I also would like to suggest you to make a big bracket like this, because everything inside here belongs to the sine function. Okay. So in angle modulation, theta t is prescribed as a function of modulating signal. So theta t is a function of VMT. Okay, it's a function of VMT. So in equation 3.1, you're gonna see that the parameter f, the parameter theta, and also the frequency of the carrier varies according to the time. Okay, so VMT, we still use the same VMT like in the AM, where it is equal to VM sine 2 pi FMT. Okay, so there are a few parameters that you should understand. The first one is what we call as the instantaneous phase deviation. Okay, instantaneous phase deviation is the instantaneous change in the phase of the carrier at a given instant of time and indicates how much the phase of the carrier changed with respect to its reference phase. So instantaneous phase deviation is equal to theta t, and the unit is in terms of radian. Okay, so this is from the general equation of this one. Okay, so theta t from the general equation is the instantaneous phase deviation. Okay, the first parameter. Okay, while the instantaneous phase second parameter is the precise value of the phase of the carrier at a given instant of time. Okay, so it is omega ct plus theta t. So this is actually 2 pi f ct plus theta t. Okay, so this is a instantaneous phase, and the unit is in terms of radians. Okay, so if you see the general equation here, that means 2 pi f ct plus theta t is actually the instantaneous phase. Okay, so the thing in the bracket, okay, all the things in the bracket here is what we call as the instantaneous phase. Okay, then we can look into the third parameter. Okay, third parameter is what we call as the instantaneous frequency deviation. So Instantaneous frequency deviation is instantaneous change of the frequency of the carrier and defined as a first-time derivative of the instantaneous phase deviation. So this is actually the instantaneous change of carrier frequency according to the input at a specific time. Okay, so this is actually d dt of the instantaneous phase deviation. Okay, so d dt of theta t, okay, will produce theta prime t. Okay, so theta prime t, the unit is radian per second. Okay, or simply as hertz. Okay, then number 4, instantaneous frequency is the precise value of carrier frequency at a specific of time based on the input variation. Okay, so that means d dt. Okay, if you deviate the deviation of 2 pi f ct plus theta t, okay, would be the instantaneous frequency. So what you will produce is actually 2 pi fc plus theta prime t. Okay, so the unit is radian per second. So yeah, so this is the so we already see this instantaneous frequency. So it is actually 2 pi fc plus theta prime t radians per second. Okay, so here is the explanation about frequency modulation and also the phase modulation. So if we recap again what we have learned in the beginning of chapter 3, frequency modulation is the process of changing the frequency of the carrier in accordance with the amplitude variation of the input signal. That is the FM. While for the phase modulation is defined as the frequency modulation, phase modulation, PM, is the process of changing the phase of the carrier in accordance with the amplitude variation of the input signal. Simple as that. So you don't need to memorize every words, every sentence from the lecture notes. Okay, you just need to understand the keyword of the answer. So the next parameter is what we call as the deviation sensitivity parameter. Deviation sensitivity parameter is a constant parameter. It is fixed. Okay, so we have what we call as the phase deviation sensitivity parameter and also frequency deviation sensitivity parameter. So first of all, we need to understand the equation of theta t. So previously we know that theta t is a function of VMT, is a function of modulating signal. So theta t is equal to Kp VMT. So Kp is what we call as the phase deviation sensitivity parameter. Okay. And then frequency modulation parameter theta prime t. Theta prime t is equal to Kf VMT, where Kf is the frequency deviation sensitivity parameter. Okay, so we have Kp and also the Kf. So what is Kp? So Kp is a parameter that define the phase difference divided with the voltage difference of the carrier. Okay, so you see that this is actually the unit for kp is radian per volt. Okay, so kp is actually delta theta, the difference in terms of phase of the carrier divided with the difference of voltage of the carrier. Okay, whereas for kf, the unit is radian per second per volt, and it is actually equal to delta omega, the difference of omega divided with the difference of voltage of the carrier. Okay, so we have asked this question in the final exam, where we will give the value in the form of table. So for example, I give you a table like this. So for example, this is omega, this is the voltage. Okay, so imagine that if we have x1, x2, x3, for example, and then here we have y1, y2, y3. Okay, so in order to find the kf parameter, so it is equal to x1, sorry, x2 minus x1 divided with y2 minus y1. Okay, or you can also do like this, x3 minus x1 divide with y3 minus, sorry, you can minus with the adjacent value. Okay, you can minus with the adjacent value. This is true. Okay, so you can choose either of these. Okay, divide with either of these. Okay, so we'll get the value, a value in terms of radians per second per volt. Okay, so in the previous exam, we have given this question before. We give a table and you need to find either kf or kp. Okay, similar for kp. If it is for kp, we will give you a theta parameter over here. Theta parameter in terms of x1, x2, x3, and also the voltage parameter. So you need to find the kp. So for kp, the unit is radians per volt. Okay. If you see the equation on the right about the integral. So if you remember previously that I mentioned theta prime t is equal to d dt of theta t. Okay, so if you do the deviation, then that means if you want to find theta t, okay, that means theta t is an integral of theta prime t dt. Okay, which is like this. Okay, so if you see from here, integral of theta prime t, integral of kf vmt. So since kf is a constant parameter, we can put outside, okay, and we can integrate the vmt. So vmt is a sine function. So if you integral sine function, you're gonna get negative cos, okay, which we're gonna see later after this, okay. So now we're gonna see the equation for the phase modulation. So what you're gonna learn is about phase modulation and also the frequency modulation. So from the general equation, we can produce the phase modulation equation, which is equal to VC sine omega CT plus theta T. So I suggest you to make a big bracket so that you are not making careless mistake. Okay, omega CT is actually 2 pi F CT. Okay, plus theta T. So theta T here is, if you see, this is Kp VMT. So this is actually Kp VMT. Okay, so it looks like the equation below. So Vc sine omega 2 pi FCT plus Kp Vm sine 2 pi Fmt. Okay, so this is the general equation for phase modulation signal. Okay. However, for the frequency modulation, how can we get the frequency modulation equation? Frequency modulation equation is equal to Vc sine in bracket omega Ct plus theta prime T. Okay, so in order to do this, we can find the theta T from theta prime T. Okay, so therefore it is Vc sine omega Ct plus integral of theta prime T dt. Okay, so theta prime T dt, as we have seen previously, is actually Kf Vmt. So you can put outside Kf Vm because this is a constant parameter. It's a fixed parameter. And we can integrate sine omega mt. Okay, sine omega mt, we can do the integral. So sine omega mt is actually produce integral of sine. You're gonna get negative cos divide with omega m. Okay, so this is actually equal to Vc sine big bracket omega Ct is actually 2 pi F Ct. Okay, minus Kf Vm over omega m. Omega m is 2 pi F m, 2 pi Fm. Okay, cos omega mt. So this is cos 2 pi Fmt. Finish. Okay, so this is the general equation for Fm signal. Okay, so in this example, you need to derive the PM and FM signal using cosine wave signal. Okay, so if you're using cosine signal, that means the general equation should be cosine and the VMT also should be cosine. Okay, so that means initially it looks like this, initially. So that means the general equation. So previously you see that if I go back to the previous slide, okay, so in other literature books, we can also use cosine. Okay, so if you're using cosine, make sure the general equation is cosine and the VMT also in terms of cosine, so that easy for your calculation. So in this example, if you see, the general equation is in terms of cosine. The modulating signal is in terms of cosine. So to produce a PM signal, so it is a straightforward. From the general equation, we can put the value. So Vc cos big bracket omega Ct, or you can write 2 pi Fct plus Kp Vmt. Okay, where we can define this as Vc cos in bracket 2 pi fct plus kp, the phase deviation sensitivity parameter, the peak amplitude of the modulating signal, cos 2 pi fmt, and then close big bracket. Okay, this is for PM, phase modulation. And if you see for the to produce the FM signal equation, okay, if you see to produce the FM signal equation, so therefore from the general equations, Vc cos omega ct plus theta t, so we change theta t is equal to integral of theta prime t dt. Okay, what is theta prime? Theta prime t is equal to kf Vm cos omega mt. Okay, so kf Vm cos omega mt, so we can do the integral, and then we can put outside kf Vm, and then integral of cosine. Integral of cosine, you're gonna get a positive sign. Okay, so positive sine over omega m. Okay, so therefore your answer is Vc cos in bracket omega ct plus kf Vm over omega m sine omega mt. Integral of cos, you're gonna get positive sine over omega m. So this is actually 2 pi fct plus kf Vm over 2 pi fm, okay, sine 2 pi fmt, okay, and then you close big bracket. Okay, so this is how we define the equations for FM and PM. Okay.
Sure.
Yeah.
For KF, kan
Okay.
dia punya unit SI radian over VN.
For KF tadi kalau kita this one radians
No,
per second per
radian
volt.
per second over VN. So to calculate the equation tadi, yang equation in radian or in degree. To calculate.
In radians or in degree?
Calculator tu kan, change to radian or stay with degree.
Based on the question, I think. So normally
Based
we
on the question.
if you see in most of the calculation, normally we use the radians.
Radians.
Okay, normally we use the radians. So don't worry. Later we're gonna see the example. You're gonna see from what happened from there. Okay. So normally, if you are given the frequency, so you need to find the 2 pi fmt. So normally in the question, we are not asking you to find you are not going to solve the whole equations, because normally we don't ask you, we don't give the t value, the time value. So if you are given all the value here, that means you need to use the radians in terms of radians parameter. So nanti later you're gonna see that normally in the question we only ask student to produce the equation. Okay, not until the calculation of the radians. Okay, so you're gonna see later in the example I will show you. But to answer your question, normally we use the radians. Okay. Okay. So okay, so from here, from these equations, we can see that yeah. So this is the graph here to show the frequency deviation of the carrier. Okay. So if you see the line here, so if I draw this line, so the carrier actually center at FC, the carrier will deviate from FC to the maximum frequency FC plus delta F. And FC also deviates towards minimum frequency FC minus delta F. So the carrier frequency deviation is actually depending on the input signal. Okay, so the input signal in the center, if you see a sine wave, this one, a sine wave starting from here. So when the input signal varies from 0 until it reach the peak value here is Vm. So what happened to the carrier frequency? The carrier frequency would be maximum, Fc plus delta F. Then the input signal move towards 0. So whenever the signal move towards 0 axis here, so the carrier would be at center, which is Fc. Then the input signal move towards negative peak, negative Vm. What happened to the carrier frequency is that it's going to be minimum frequency, Fc minus delta F. Then the signal moves towards 0 axis. So the carrier would be at Fc. Okay. So this is at Fc. This also at Fc. Okay. So if you see from here, this is the graph. So these graphs will show you the difference during the process. Okay. So if you see the picture, the first picture is VCT. Okay. The second picture is actually VMT. The third picture is actually VFMT. The fourth picture is VPMT. Okay. So if you see from here, class, if I just give you picture 3 and picture 4, picture C and D, it is difficult for you to differentiate whether this is FM or PM signal. Okay. If you are only given two signals side by side, you cannot differentiate whether this is FM or this is PM because it looks similar. Okay. In order to differentiate, we need another two reference signal. Okay. The first one is the carrier and the second one is the modulating signal, the input signal. Okay. So if you see the carrier signal is a high frequency variation signal compared to the modulating signal, it has a low frequency because the ripple is far away from each other. So that's why it is a low frequency. So the key changes, okay, you're going to see later that the key changes of the carrier happens during the peak amplitude or during the zero crossing. Okay, either maximum peak amplitude or during the zero crossing, there are going to be significant changes at the output. So how does it happen? So let's go through one by one. So let's go through picture C. Okay, picture C. So if you see at the beginning, okay, at the beginning, before we have the input signal, carrier frequency would be at rest frequency. Rest frequency means it is located at Fc. Okay. Then we have the input signal starting from 0 until maximum positive. Okay. So at maximum positive, we're going to see that the output would be at maximum negative deviation. What does it mean? Negative deviation means that the frequency of the carrier at this point would be at the minimum, which is Fc minus Fm. Okay, it would be at the minimum. Then the input signal move from maximum positive towards zero crossing. Zero crossing means the x-axis. So when the input signal reach the zero crossing, what happened at the output? The output would be at rest frequency. Rest frequency means at this point, the carrier would be at frequency Fc. Okay. Then the input signal move again towards negative peak amplitude. What happened to the output? The output would be at maximum positive deviation. Maximum positive deviation means that the output carrier, the output signal, sorry, the carrier signal would be at frequency maximum, Fc plus Fm. Okay, maximum peak. Okay, so if you see from here, okay, so if you see from here, so this is sorry, maybe I should use different parameter. So let me change to delta F, because we don't know how much would be the changes. So this is actually Fc minus delta F. Okay, and then this gonna be Fc plus delta F. Okay, so we don't know how much is the delta F. It depends on the parameter given in the question. So you see that at maximum frequency, you can see that the ripples is close one another. Okay, dia punya gelombang tu rapat-rapat. So that means it is a high frequency. If the ripple is far away from each other, that means it is a low frequency. Okay, so then the signal move again towards zero crossing. So at zero crossing, the output frequency would be at rest frequency, which is at Fc. Okay, and so on. The signal will repeat the cycle again. Okay, so this is what happened for the FM signal. And for the PM signal, if we go through the picture D, so for PM, you're going to see that the critical change only happened during the zero crossing. Okay, so if you see at the beginning, it is a rest frequency where the carrier would be at Fc. Okay, then we have the input signal starting from zero. Okay, so it is actually, if you see that the signal move towards positive, so maybe I can erase this one so that, okay, so starting at zero, you're going to see that the signal would be at maximum positive deviation. So at this point, you're going to see that it is actually Fc plus delta F. Delta, I can put delta theta. Okay, delta theta. We can also make it similar, Fc plus delta F. So I'll make it the same so that you can see the difference in terms of frequencies. The frequency is higher, okay? And whenever the signal, the input signal move again towards positive peak, what happened to the output? The output would be at rest frequency. Rest frequency means at Fc. Okay. Then the input signal move towards zero crossing. So you see that the signal is moving from positive towards negative. That means the output gonna be at maximum negative deviation. Okay, the signal is moving from positive to negative. So the output will be at negative maximum deviation. So it is actually Fc minus delta F, the minimum frequency. Then the signal reach the peak amplitude, the negative peak amplitude. What happened at the output at picture D? It would be at rest frequency. At rest frequency means that at this point, the carrier would be at FC frequency. Then the input move again. Now it moved towards zero crossing from negative towards positive. So what happened at the output? You're going to see that the output will have maximum positive deviation. Maximum positive deviation means that the carrier would be at maximum frequency, which is FC plus delta F. Okay, and the process repeats again for the next cycle and so on. Okay, so you see that as a conclusion, we can say that for frequency modulation, the critical change happen during the peak amplitude of the input signal. Okay, for the frequency modulation. However, for the phase modulation, the critical change happen during the zero crossing of the input signal. Okay, so this is about the difference between FM and PM. So if you see from here, phase deviation and modulation index. So now we want to go through the modulation index. Modulation index is represented by parameter beta. Okay, parameter beta is the modulation index. So now we have two types of modulation index. We have phase modulation index, beta P. Okay, so from these equations, VPMT is equal to VC sine in bracket 2 pi FCT. So this is 2 pi FCT plus KP VM sine 2 pi FMT. Okay, so if you see from here, beta P is representing KP VM. Okay, beta P is representing by KP VM. So please correct your note. This one should be capital V because this is a constant parameter. Okay, so this is about beta P. Okay, we also gonna have beta P. If you see beta P, the modulation index for phase modulation has a unit of radians. Okay, the unit is radians. If you see Kp is actually radians per volt. Okay, Kp parameter has a unit of radians per volt, and you multiply it with Vm. Vm, the unit is volt. So that means if you see radians per volt, you multiply it with volt. Okay, so you're going to produce a value in terms of radians. Okay, so the value of beta P is in terms of radians. And for frequency modulation, if you see from here, from the general equation of FM, Vc sine omega Ct. So this is 2 pi Fct plus minus, if you remember, over here is actually Kf Vm over 2 pi Fm or omega m cos omega mt. So this is 2 pi Fmt. Okay, omega m can be represented as 2 pi f. Okay, so don't be confused. So beta f in this example is represented by Kf Vm over omega m, or Kf Vm over 2 pi Fm. So beta f, if you see, beta f is actually a unitless parameter. Okay, so if you multiply Kf Vm over omega m, So kF, the unit is radian per second per volt. You multiply it per volt and you divide with radians per second. So it is actually like this, radian per second per volt. You multiply with volt and you divide with radians per second. Okay, so this can be cancelled out, and radians per second and also radians per second can be cancelled out. So that's why the output is a unitless parameter. Okay, it's a parameter without a unit. Okay, so beta f can also be represented as this parameter, kf vm over fm. Okay, so if you are given kf parameter, in terms of hertz per volt, okay, so you can use this equation. Okay, it depends on this, okay. So previously is kf equal to radians per volt, equal to radians per volt. Okay, radians per second per volt. Okay, so if you are given in terms of hertz per volt, then you can use the second equation. I can say that this is the second equation. Why it looks a bit different? Because kf now is in terms of hertz per volt. So therefore, you multiply it with Vm and then you multiply it with Fm. So you get a parameter in terms of a value without a unit. Okay. So radians per second per volt, if you divide with 2 pi, okay, if you divide with 2 pi, you're gonna get a value in terms of hertz per volt. Okay, so this is actually similar that from the previous. It's not different actually, because the kf parameter, if you divide with 2 pi, is gonna be in terms of hertz per volt. Okay, so normally in the exam we will give you this equation. We will give you this the question related to this equation. So beta f, normally we use this equation, is equal to kf vm over fm. Okay, so kf vm over fm. Okay, so this is what we normally use to answer the question in the exam. Okay, so I stop here so that you can go to the next class and we can take the attendance. So you can open your QR code. Okay, you can open your QR code. Okay, you can scan the attendance and then you can go anywhere you like. Okay, see you again after the semester break. Okay.
Thank you, Doctor.
Okay, welcome.
Okay, Doctor. Thank you.
Thank you,
Welcome.
Doctor.
Okay, welcome. Next week will be semester break, right? So we're gonna meet again
Yeah.
after semester break. Yeah.
Okay, Doctor. Happy
Okay,
holiday.
welcome. Okay,
Bye bye,
welcome.
Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Doktor,
Ya.
saya tak dapat scan lah.
Nama siapa?
Aina Syahmi.
Aina Syahmi. Mana Aina Syahmi? Okay, done. Settle.
Saya pun doktor.
Ahmad Mustafa.
One by one. First, siapa?
Eli Mazira.
Ellie. Ellie Mazira. Okay, done.
Thank you doktor.
Okay.
Ahmad Mustafa.
Pardon? What's your name?
مجاهد عبد الله.
I
Ahmad
cannot
Mustafa.
hear. I cannot hear your voice. Can you repeat again?
Ahmad Mustafa.
Ahmad Mustafa. Okay, Ahmad Mustafa done.
مجاهد عبد الله.
Ahmad Mustafa. Yeah.
What's your name?
مجاهد عبد الله. مجاهد.
Mujahid. Where's your Mujahid? Okay. Okay, done.
Thank you doctor.
Thank you.
Okay, welcome.
Saya Dr. Shazrina.
What's your name?
Shazrina.
Shazrina.
Yeah. Yeah.
Okay, dah settle.
Thank you doktor.
Okay, who else? Any more?
Thank you doktor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome. Any more? So everybody has scanned the attendance. So if you have scanned the attendance, huh? Settle everybody settle So
Saya belum doktor, saya belum.
Oh, belum. Siapa nama?
Afif.
Nama penuh apa?
Afif Jazimin.
Afif
Bidang
Jazimin.
siasatan
Okay,
leader.
Afif.
Ya betul.
Okay, Afif, just settle lah.
Alright, thank you doktor.
Okay. Any more? Okay, so we can assume 3 students absent.